Good evening, sharks, and we would like to introduce to you a novel invention based on the morphology of frog limbs. We are the Wiley Wallabies, and we will bring you a brand new innovation that you will love to invest in. So this is our inspiration for our new innovation. We researched this paper that detailed frog climbing abilities based off of the structures of their hands. The objective of this paper was to determine the types of forces used for tree frogs to cling to cylindrical objects such as trees, as opposed to previous studies that were focusing on flat surfaces. Their methodology involved using force transducers on restrained frogs by holding cylinders and took scanning electron micrographs of the limbs to understand the fine structure of these toes. The results showed that friction and normal forces were used equally, and the frogs had more contact area beneath the toe pad, also known as the tubercle. While smaller size and shallower cells, proximal location in this area helped reduce the shear stress. Alternatively, when holding a flat surface, only adhesive toe pads were used. We then conducted a discovery decomposition that tested the hypothesis. The hypothesis showed that it was true indeed that the tubercles were more important than the toe pads, and we used this information to create our innovation.
Next, we're going to talk about the modifications that we made based on the paper that Nick just described. So we added some soft, flexible material to the toe pads in that tubercle location that Nick was talking about to increase our amount of grip and friction on the design. From this first video, you can see the softness of the material when pressed on. In the second video, you can see some of the texture that we added to this material in order to get the same texturing and surface finish that a frog has. Next is our analogy check. Here we can see some of the similarities and differences that we expected to see from this design. A lot of the similarities were we were hoping to increase the grip on curved surfaces. We were hoping to increase that the contact of surface area between this location, and we wanted more stress when you pulled against it.
All right, moving on to our prototyping process. We used the Lulzbot Mini and Taz for our fabrication, and we used two types of PLA, one rigid and one of a flexible variety. Initially, we were not able to get the functionality we desired as we ran into issues with tensioning. We attempted to tension the first prosthetic that you see on the left with rubber bands, and it did not provide the desired functionality. Onto the second model that we developed, we used an existing model that suited our needs far better. We added better tensioning with the use of threads that looped around the distal connectors. And we also added rubber bands behind the fingers. As you can see here, they are tied right where the strings connect. That provided the necessary flexion to pull the hand back into place after tension from the strings was released. Moving on. Right, so here's a quick demonstration video showcasing how the hand functions. We can see that pulling onto the strings is causing all the fingers to curl together. Also, we added the silicone pads to the base of the digits, much akin to where you would find them on the tubercles of a frog. And we can see that the fingers all curl together on the pulling of the string, and not showcased here is the snapping back of the fingers as a result of the rubber bands. Not only does this help in grip and adhesion, but also allows the user to allows more mobility compared to the previous prosthetic.
We also got the opportunity to test our prototype. Here on the right, we can see a picture of our prototype test setup. We curled the fingers around a bottle shape that most humans would want to use, and we tested the slipping in the downward direction, so the y-axis direction, and replicated the testing that was done in the paper. And we used a force gauge to determine at which force the slipping started to occur, and this allowed us to test the max tensile force. Our quantitative results were really promising and supported the benefits of our design. As you can see on the blue line, that was without the pads, and the yellow lines were with the pads. And we can see approximately a 1 to 1.5 Newton improvement, which is pretty significant here. Our results are also fairly consistent, which shows really the promising technology and that it should be further developed.
So one of the major benefits of our prosthetic is the majority of the force is able to be exerted on the lower and inner parts of the fingers, which allows items with smaller cross-sectional areas to be gripped with ease. And most prosthetics rely on the entirety of the fingers to grip and pick up objects. So because of the modifications we've made, gripping skinnier objects has become far easier. In the future, we would like to expand the silicone pads down to the palm of the hand, just to increase the grip that the user would have, as well as making the pads adjustable to pertain to specific uses such as driving or climbing ladders or sports that could be interchangeable, and adjustable pads for different people's hand sizes. A prosthetic hand with superior functionality would make a large impact on people's lives, and we believe our hand has a promise to make a great impact for multiple functionalities. Thank you.